Welcome back to the second part of the third experiment. In this part, we will design a lead compensator to improve the transient performance of a transfer function or a system. So let's get started. So in the last part, we have seen the use of a lag compensator. We designed the lag compensator. For the lead compensator, the transfer function is basically the same, a gain and a 0 and a pole. The difference here is this time the pole will be greater than the zeros. So we will design or choose this PC and ZC in such a way that the condition that we are given are met. So let's get to the problem. So in this experiment we will need to analyze or use this transfer function. So this is basically the same as the previous, or just a bit different, I guess. It says that GS is equal to 1 by S plus 1, S plus 2 and S plus 10. So there are basically 3 poles at minus 1, minus 2 and minus 10. I encourage you to draw the root locus of this transfer function on your own, but I will for the experiment use the R locus function of MATLAB. So let's get forward. So in this part we will design a lead compensator. As I have said, the lead compensator have the same function as the lag compensator, as you can see here. The same function, but the difference will be in the Z lead and P lead, which are the zero and pole location of this transfer function. Our task is to again keep the overshoot at 20%. So the zeta will be again 0.4559, as it is the same function. So, and we have to reduce the settling time, or TS, twofold. So our task here is to improve the settling time by a factor of 2. That means if previously the settling time is 10, now the settling time will be 5. But we have to keep the overshoot at 20% fixed. So let's move forward. So at first we have to draw the root locus. We will use let me just open my sketchpad. So yeah, we will need to draw the root locus first, and we will use our conventional R locus command. R locus of G will be the open loop transfer function, and we will obviously use the S grid. So two commands that we will use are R locus and S grid. We will use these two straight away without any delay. We will use this straight away. So in the S grid we will use our zeta, which is 0.4559, 456 for simplicity, and R locus will plot this one. So again we will use that rlog find command to actually get the cursor on, and we will place the cursor on the intersection of these two lines. So let's analyze this root locus first. So there are 3 poles at minus 1, this one is at minus 1, minus 2, minus 10, and this is our 3 branches of root locus, and this is the S grid line, of course, this line. So we will need to place our cursor at the intersection of these two lines. The first one is the red line of root locus, and the other one is the dashed line of the S grid. So by this we will choose this point. Now whenever we choose this point, the rlog find command will give back the K, or the gain, and the poles associated with this. So you can see we'll get 3 poles. 2 will be here, and another one will be in this position. So now we have these two are our dominant poles, and they are complex conjugate of each other. These are called the dominant poles, S1 and 2. Now this is the uncompensated system, and we need to improve the settling time by 2, a factor of 2. So what can we do to increase the settling time or improve the settling time a factor of 2? Let's analyze it. So as I have said previously, settling time is TS, which is 4 by zeta omega n. Again, I have mentioned that zeta omega is the real part of the complex conjugate pole pair. So it is something like 4 by real. So the real portion of the complex pole is now 1.1849. So settling time will be 4 by 1.1849. Whatever it is, you need to decrease the settling time by 2. So let's analyze this from a different perspective. We know that settling time is 4 by real. If we want our new settling time Ts prime to be a half of Ts, and we just put the value of Ts here, we can see that to achieve our desired result of new settling time, which is half compared to the previous, we will need to multiply the real part of this pole by 2. So if this is the original pole, now we will need to multiply it by 2. Now remember one thing, multiplying the real part by 2 is enough, but one condition was we have to keep the overshoot at 20%. We cannot change that. So let's say for demonstration purpose, this was our original pole. Just for demonstration purpose, our original pole is this one. For better view, I am choosing this point. If I am increasing the real part by 2, then imaginary part is kept constant. So this is the real portion. So if I increase it by 2, it will come here. Imaginary part is kept same. So this will be something like here. So this will be our new pole. But as you can see, this pole is not on this line, this dashed line. But if we want to keep our overshoot fixed, our new pole must be on this line. So if we multiply the whole pole by 2, then this will just shift to the new position, let's say here. Or now I can choose my real pole. So let's say this was our real pole. If I multiply the whole pole by 2, then the real axis segment will become double and the imaginary axis segment will also become double. So it will be something like here. So this is our new pole. So our task is to build a compensator, or a compensator actually means that we are adding S plus ZC by S plus PC. That means we are adding a 0 and a pole. We have to add a 0 and a pole in such a way that our root locus travels through this point. At present, our root locus is not traveling through this point, but we want our root locus to travel through this point. That's our ultimate task. So let me just clear away the unnecessary things. So let's say this is our new, for example, let's for simplicity, let's just say this is our new pole. So we want our root locus, after incorporating the compensator, we want our root locus to flow through this point. Now we are adding 1 0 and 1 pole, right? We have to be a bit smart to actually achieve a faster result. Let's say we have 3 poles here, and as you can remember from the theory class, if any random point is on root locus, then at that point contributions from all the poles and zeros equate to an angle of -180. Let's say this is a random point at root locus at present. So if I just consider the contribution from these 3 poles, let me just change colors. Oops. So these are the 3 lines joining the desired point and the poles. If we take these angles, this angle, this angle, and this angle, let's say theta 1, theta 2, and theta 3, then these are poles, so angle will be negative. So minus theta 1, minus theta 2, and minus theta 3 must be -180. This is the condition. So if we want any point to be on root locus, then the contribution of all the angles from all the zeros and poles at that point must be equal to minus 180 or any odd multiple of 180. So now for the contribution of poles it will be negative. For the contribution of zeros, there are no zeros, so there are no positive here, but if there is a zero somewhere here, let's say this is another zero, at that case this contribution theta 4 will be added, it will not be minus, it will be plus. Okay, so now let me refresh. So this is our new pole. We have found it by multiplying this by this with 2. We want our root locus to go through this point. So at this point the contribution from all the poles and zeros of the system should equate to minus 180. There are already 3 poles here, so let me just draw them. 1, 2, 3. So let's say this is theta 1. Let me just color them. Let's say this orange one is theta 1, this yellow one is theta 2, and this ash one is theta 3. So we already have theta 1, theta 2 and theta 3. As they are all from poles, they will be all minus sign. Okay. Now we are adding 1 0 and 1 pole. Our ultimate target is that the contribution from all the poles and zeros at this point will be minus 180. We have a liberty to choose either the zero or the pole. There are all poles here, so for the simplicity of the calculation, let's say we are placing the new zero at s equal to minus 2. How will this save our lives or make our lives easier? So there is a pole and a zero at the same point. That means is you don't have to calculate the angle contribution of this pole and zero, because let's say this will be theta 4. You can see that theta 2, let's say this is theta 2 for the pole and the theta 4 for the zero. You can see that theta 2 and theta 4 has the same numerical value, but they are of opposite signs, so this will be cancelled out. So we don't need to calculate for s equal to minus 2 anymore, not for pole, not for zero. So this makes our lives easier. Then we have to choose our pole somewhere. Let's say we are choosing our pole here. Just choose an arbitrary point, because we will calculate this by doing some calculations. So let's say this is a random point. So contribution from here is theta 5. So minus theta 5. That means our final equation is minus theta 1 minus theta 3 minus theta 5 equal to 180. By some simple calculation, we can determine this theta 1 and theta 3 by, if we know theta 1 and theta 3, then by solving this equation we will get this angle actually. So let's see. So this is the calculation. This is how you will need to do it manually. This A is the new desired point. As you can see, we have this point C, we have P, and we have PC. You can notice that there is no point at s equal to minus 2, because we know that we have placed a 0 here. So the effect of pole and zero cancels each other, so there is no line drawn from this s equal to minus 2, that desired point. There are only 3 lines, one from s equal to minus 1, one from s equal to minus 10, another one at s equal to minus PC on our desired pole location. So let me just use okay, so theta 1 is this angle, theta 2 is this angle. So you can easily calculate theta 1. Theta 1 is tan inverse of this value by this value, AD by BD. You already know AD because A is our new pole, right? A is our new pole. So we already know the pole location A plus IB or JB. So we already know the pole location. So if it is A plus JB, then this is A and this is B. So by this we know the value of B, and we also know the value of this portion, which is 10, because it is S equal to minus 10. So we can write that tan inverse 4.64 by 10 minus 2.36. How we are getting these values? Please remember that our original pole location was minus 1.18 minus 2.32. So we need to multiply it with 2. After that we will get this value. You can see minus 2.3698 plus minus I or j, whatever you tell it, 4.6498. So in this figure, this small portion is 2.37, and this portion here, AD, this portion is 4.65. I'm just rounding it a bit. So you can easily calculate theta 1. Again, I'm calculating this tan inverse of 4.65 by this value. So this is basically 10 minus 2.37. 10 minus 2.37. So you can get the theta 1 from this calculation. Theta 1 is 31.65 degrees. Done. In the similar manner, you can also calculate theta 2. Theta 2 is basically this angle. You can easily calculate this angle because this angle is theta 2 prime, and this is tan inverse of just simply 4.64 divided by this whole thing is 2.32 or 36, and this small portion is 1 obviously. So this one you can easily calculate. And finally, the original angle theta 2 will be 180 minus this whole thing. So you can calculate it to 106.41. So finally, minus 31.35 minus 106.41, and this is also a pole. So minus theta is equal to minus 180. If you just solve this equation, your theta will be 42.24 degrees. So now you know that this angle here is 42.24 degrees. So tan theta is equal to AD by this whole thing PCD. This is PC and this is D. AD by PCD. We already know AD, we already know theta, so we will know PCD. And PCD is basically PC minus OD. And we know PCD from this equation. We know OD because OD is basically the real part of the new pole. So we know OD. So we will get PC, and PC is the pole location. Whatever the value of PC is, we'll just put a minus. So PC is at 7.49. So finally, our original the equation of our compensator will be this one: K into S plus 2 by S plus 7.49. S plus 2 was because we have chosen a 0 at minus 2 for the sake of the simplicity of the calculation, and by calculation we have found out that our pole location is at minus 7.49. So this is our transfer function for the lead compensator. It has a gain in front. We will find the gain by unlock find command, of course. So as you can see, I'm just going through the command here. I'm not going to the MATLAB again. So this was the first piece of command. This is the same as the previous one. You can just use the R locus to plot the root locus. You can draw the dashed line by S grid for a particular zeta or overshoot, and by unlock find you can specify the point, and that will give you the K and for the gain and the poles. As you have the gain now, you can set up the closed loop system, which is gain multiplied by the open loop function and the negative feedback, so G1, and then you finally can plot the step response of it and the step inf also. So that's done. This is the step response. You can see there is a certain amount of error as well, but we are not worried about the error. We are worried about the settling time here. So we need to reduce this. Now we have designed our new pole by just multiplying it with 2, and then we have calculated the poles and zeros manually. And for the next part of code, we have our controller GC, and this is a compensated system. So we will multiply our original open loop function with the compensator s plus 2 by s plus 7.49. Again, we will plot the root locus of the open loop system. We will plot the dashed line for a particular zeta with sgrid command. We will again identify the intersection of our root locus and the sgrid line with rlog find. It will give us the gain and the poles. We need the gain, of course. So the gain is then multiplied by the open loop function gc, which is the compensated open loop, and by giving a negative feedback to it, we finally get our closed loop g2. Then we plot our step function and we get the stepping as well. So this is our compensated step response. You can see that the error has not improved a lot, but settling time should increase. Settling time should increase. Sorry, I'm sorry. Settling time should improve. So this is our the settling time here is 1.6648, and for the previous case the settling time was 3.2858. So you can see there is a fair amount of decrease in settling time. Actually, improving settling time means you are decreasing the settling time, because the sooner it will settle, the better it is. So for uncompensated system, the settling time is 3.28, and if I divide it by 2, it will be something like 1.6. For our compensated system, the settling time is 1.66, so it's pretty accurate. Our design is pretty accurate. We don't bother about steady state errors here, because for improving steady state errors, we need lag compensator. That's all for a lead compensator. You have the homework attached to it. I hope you will be able to do this by the knowledge you have gained from this lecture. Thank you.